Okay. Um, how many people were here last time? I know it was the World Cup, so there was less amount of people, but could I get a show of hands of who was here? Okay, okay. Okay. Um, so that's okay if you guys missed. Uh, because we just went over like a baseline of what kinetic and potential energy was. Ethan, do you want to put in chat like a quick summary of what kinetic and potential energy is? So let's get started. Tell okay. Okay. So welcome to Intro to Physics again today. Today will be like all over the place. The homework from last class was you can still do the homework. The homework's mainly for you guys. If you guys don't feel like you guys need to do it, that's okay, but that's to get more practice in. So, hmm, sorry. Sorry about that. Let's go here, right? So last class we talked about covering kinetic and potential energy. So a quick rundown of what each of them are. Ethan put it in chat. Kinetic energy is just the energy an object has when it's in motion versus potential energy where it's just stored energy. And you can kind of think of it as a roller coaster, right? There's a lot of potential energy when it's at its top, but as soon as it goes down, then it's all converting into kinetic energy, right? And I forgot if we did these last time. I think we did do these last time, but if you guys weren't here, I'll just go quickly over it. Um, I'm hoping you guys have a pencil and paper or notebook ready because there are the two equations we need to talk about, kinetic energy and potential energy, right? We'll be using this a lot this class. So kinetic energy is just equal to 1/2 mv squared, where m is equal to mass in kilograms and velocity is just meters per second. And then potential energy is equal to just mass times gravitational acceleration times height, right? And something you guys should know is gravitational acceleration, which is just portrayed as g, is just equal to 10 meters per second squared, right? Um, so when we're talking about question two here, this is the question we did last time for the people who weren't here. We're only going to be using the kinetic energy formula. I don't want to go through this again because I think it'll like take 2 seconds to do together. But so if we look at the first part, 1 kilogram ball at 4 meters per second, 1/2 times 1 times 4 squared, correct? So you have 8 as your answer to this. And then this one, 2 kilograms at 2 meters per second. It's just 1/2 times 2 times 4, which is what? 4. So clearly a 1 kilogram ball at 4 meters per second has more kinetic energy according to these equations that we built. And again, something I should reiterate from last class is energy always, kinetic energy and potential energy will always be measured in joules. That's the unit. Do you guys have any questions about this so far? Or I know I'm going a bit fast, but I think for the people who G is gravitational acceleration. So sorry, G is just equal to 10 meters per second squared. It's the acceleration we face to gravity when like, run. Are we good? Yeah, okay. I'll move on then. Good. Okay. Oh, and let's just do question three, really quick. So, how does raising an object higher affect its PE? So we know that clearly mgh is the equation for PE, and we know that if we raise it higher, that's just increasing its height, which just increases the whole potential energy, correct? So that's just two equations or two questions to work with the equations. And then we went over the work energy theorem, which basically explains the relationship between work and kinetic energy. And it states like the net work done on an object is equal to the change in its kinetic energy. And we just talked about kinetic energy, right? Kinetic, so if we're thinking about the change in kinetic energy, we're just thinking about 1 half mv squared final, this is the final minus the initial 1 half. Well, minus the initial kinetic energy, correct? And in this case, the velocity could be different, the mass could be different for both scenarios, right? Let's say a box with 2 kilograms will goes 2 meters per second, but then it suddenly increases to 5 kilograms of mass and goes 4 meters per second. Then you would input these here, and you would input these here, and you would just get the difference equals the work done. Correct? Does that make sense to you guys? Yeah. I am going a bit fast because this is just review and we have a lot to cover for the next portion, but okay, good. Um, and like it could work the opposite, right? If a car's going fast initially and then it's slowing down, then it's doing negative work, correct? And another way to portray work is just the amount of force applied times the distance, which is like the more logical way I would think of it, right? If I'm pushing a box with a certain amount of force for 5 meters, I'm doing some amount of work, correct? So that's the way I would think about this equation. Like you could almost like if you don't know the formula, you could almost create it by just logically thinking about it, you know? And again, it's just all in joules. And oh, I actually use this example right here. But yeah, good, 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 good. All right. I don't think we did this. Did we do this last time? For people who were here last, you guys did this. Um, okay, how about this? I'll go through the first problem with everyone, but then let's just go through or you guys, I'll give you guys a bit of time to do the second problem. Is that fine with you guys? Because I know people who already were here last time might get a bit bored. So let's go through the first problem together. So a 2 kilogram object speeds up from 3 meters per second to 7 meters per second. How much work was done on this object? So clearly we have mass and velocity, correct? So we know this is going to be using kinetic energy. So we have 1 half, and it speeds up from the initial 3 meters to 7 meters. It even says speeds up, right? So we're going to do 1 half times 2 times 7 squared minus 1 half times the mass is the same for both scenarios, so and then times 3 squared, correct? So we can cancel this out and we're just left with 9 or sorry, 9 minus cancel this out, 9 minus 49, which equals 40 joules of work is done. Correct? Does that make sense to you guys? Good, good, good. I'll give you guys a minute or so to do the second one by yourself. If you guys aren't done in a minute, that's totally okay. I'm not expecting you guys to be done, but just to start figuring it out before I go through it. And then if you get the answer, you can message me or Ethan. Good. Oh, okay. Um, I know a lot of people didn't finish, but I hope you guys at least got started, right? There's a very condensed version. So we know that we it says assuming it starts from rest, correct? So we know that already we can just do 1/2 mv squared. We don't need to find any difference because there's no point. Like let's say we did do the whole equation. This is again final. Sorry, final. This is again initial, right? Initial. Since we know that if v is equal to 0 in the initial, this whole thing just gets canceled out, correct? Because anything times 0 is just 0. So this everything, and then we just use this. That's why I just did 1/2 mv squared here as well. And then you can solve for v to get 2 meters per second. Yeah. Um, I hope you guys got that as well. I hope this makes a bit of sense to you guys. Yeah. Okay. You guys didn't do this, did you? This is a fun one. I think with the knowledge I gave you guys, this is pretty self-explanatory. Or not, if you like, you don't need to use any equation for this type of question. You just need to think about it, I think. Because obviously I could solve this with equations, but that'd be a little too complicated right now for you guys, especially because it will take trigonometry to do this, like using sine and cosine. And I don't want to go too deeply into that right now. So try to formulate an answer and then explain to me in chat. I'll give you guys like until 24, 25-ish. Oh yeah, I'll be going over what this specifically is. I just got a few questions asking what this is. Um, don't worry about it right now. Just think of it as like normal friction because I think it's actually the next it's after this, but right now just think of this is a variable representing the kinetic friction. So you can just think of this whole thing as just friction for now, which is just opposing the motion. Like I think this will make more sense if we what I have it right here. Yeah, try your best to answer it right now, then I think it'll make more sense. Okay. Okay. I'll just Yeah, I'll just get started. A lot of you guys did answer this pretty well. I think there's some confusion, but I think once you see me kind of do it, it'll make a little more sense. So basically, we have let's draw this out, okay? A block is released from rest at the top of a rough incline. The coefficient of I'm just gonna say the friction is some variable, right? The block slides a distance d down the incline before reaching the bottom. The incline angle is then doubled while the distance d along the incline and the and some friction coefficient or some friction variable will remain the same. Which block will have a greater speed at the bottom? Or yeah, technically, yeah, that's one way to say it. Okay, so let's get started. So the first case, right? Let's just say that's too steep. Let's do this. The first case is this, right? Some angle here creates this block to go this way, right? This is the first case. I'm just gonna draw it out. Second case is then everything stays the same except for the angle, correct? The angle gets doubled. Let's say this becomes the angle. And now the box is going down this incline, correct? So when we think about it like this, I would say that the second case is gonna have a greater speed at the bottom. And I would be correct to assume so because there's more gravity. You can think of it like that. There's more gravity that can pull down on this object than here, right? Because right now with the first case, there's this block that's at a lower incline, so the block will slide a bit slower, correct? But when you have a bigger incline, there's this block has a gravity that could go down more than this one. Does that kind of make sense to you guys if I put it in a picture like that? And that's why the second case would almost always, like you can even almost think of it like like yeah, that's like when you're like thinking of these problems, it's also sometimes great if you just try to put words in English like that, right? You can almost like because this is a really easy experiment to do at home, right? If you take something with the same mass, right? I'll take like a block and then I'll slide it down an incline that's a lot less steeper. It's gonna obviously, and then you do the same thing but with a steeper hill. You'll obviously see it go down faster because there's more gravity that can interact with the block, right? If I was doing this with trig terms, you see how this side is bigger than this side here? That's corresponds with a higher speed technically because if you take sine, which is basically this side, I don't want to overcomplicate it because I don't want to lose you guys again because then you might not understand the problem. But if you take the sine of this side and the sine of this side, this is going to always be bigger than this. That's like a logical way to think about it, right? And then you don't have to worry too much about friction in this case. Yeah, good. Okay. This was a pretty hard question though, because thinking like trying to put it in English like that takes like a lot of effort. But I think we're done with but or not we're not done with, but that was like the basics of what potential and kinetic energy were. So if you guys have any questions about that, I'll give you guys like 2 minutes to ask about anything but like that I just covered. We'll go over what friction is like after these set of slides. These set of slides are pretty short. So yeah, 2 minutes, 32. Okay. Let's move on to Hooke's law. Um, so first, I think it's always important to understand the variables before we do anything with it. So there's three main variables when we're talking about Hooke's law. Force, which we've talked about earlier, right? Force, which has newtons, and the spring constant K, and displacement X. We've kind of worked with two out of these three variables already, F and X, but a new one has appeared, K, right? So when we're looking at this equation, this represents the force that a spring can output within, yeah, actually, yeah, just the force the spring can output with the amount it has been displaced, right? And when we're talking about I think the most confusing thing about this is the spring constant, right? So the spring constant is basically like it's gonna be a number. Like a lot of problems will give you what the spring constant is, but when we're looking at the spring constant, this is talking about how stiff or springy the spring actually is, right? So when something has a larger spring constant, that means it's a stiffer spring than something that has a smaller spring constant, right? And you can kind of think of it as like if something is harder to if it's harder to push a spring together, it's more stiff versus something that's easier to like versus a spring that's easier to kind of push together, right? Are we good on that? Are we good with all these variables? Yeah. Okay. Okay. So Hooke's law, like I just said, is the force needed to stretch or compress a string, right? If you look at this string right here, I'm assuming this has actually, I can't tell if that's a small or big spring. I'm gonna assume it's a big spring and it's almost made out of metal, right? So I'm assuming this would have a large spring constant because it's probably hard to compress, right? So when we're looking at a spring, I think the next slide actually does a good job. Oh, it's the next to next slide. But when we're looking at a spring, there is two directions it could go, right? I'm gonna skip to this slide real quickly. But when you're looking at this spring, right? I like this image a lot. But um, this way, this could be probably, what is this saying? Okay, this is saying that this way is positive and this way is negative, correct? So there's two ways that the forces could, my point is that there's two ways that the force could be placed. It could be negative or positive, correct? Um, so when energy is like stored in a spring, right? When it's like let's say this spring stays compressed, right? Then the formula would just be 1/2 times the spring constant times the displacement squared, correct? And this is probably very similar to another equation you've seen, right? You've seen 1/2 mv squared as well, right? And this was just the kinetic energy, right? It's almost the same thing, but with two different variables, correct? So and it's a potential energy, right? So when you're looking for the potential energy of a spring, you want to write this down, right? 1/2 kx squared, right? That's just equal to the potential energy in joules with the spring constant times the ex displacement. Um, yeah, this is just talking about this is just continuing on. When you Oh, MGH is just for like a normal object that's dropped at some, because if you look at MGH, it uses gravity, right? So when you're looking, but if we're talking about like horizontal potential energy with a spring, there's no play of MGH, so it can't be the same equation, right? MGH is only going to work for when you're dropping something from some sort of height, almost. But if you're talking about some energy stored horizontally or somewhere else like that, there's going to be different equations. So in this case, the equation is, sorry, the equation is 1/2 kx squared for the spring. Okay, there we go. Sorry. Um, does this slide kind of make sense to you guys? Like, that it's almost the same thing I talked about when we're doing kinetic energy, last class. When you're doubling the displacement, then the amount of energy stored in the spring quadruples, and both compressing and stretching the string, or the spring will increase the energy because both are storing some energy in some sense. Like here. Look, it's going this way, and if you think about it, it'll just snap back right back to there when you release it. That's just a quick overview of what like Hooke's law is and like springs in general. So now once we combine everything that we've learned about like the spring and the gravitational and kinetic energy, you can create like this equation, right? The total mechanical energy is equal to the kinetic plus potential plus the spring, right? Spring potential. And this is because we've covered a lot of the mechanical energies right now, correct? So when you're looking at it, these are some great examples that we have here. A block attached to the spring on a table here has, like in this case, we have a block attached to a spring on a table. It doesn't have any gravitational potential energy, but it has spring potential energy that can convert into the kinetic energy, 1/2 mv squared, correct? And a roller coaster doesn't have any spring potential energy, but has gravitational and kinetic, and a spring launcher on a hill could have all three. Mm. Okay. Yeah. Um, so why does this matter, right? If you're looking at conservative forces, right? This only works with conservative forces, right? Where the work or the where the we'll talk about what conservative and non-conservative forces are a bit later, but this is the total mechanical energy only works bec when like there's no energy lost in the process. Obviously, when we're on Earth, there'll be some energy lost to like heat or sound or air resistance or whatever, right? But in this case, and when we're talking about problems, we're using like an ideal example, right? So some examples of conservative forces are like the force of gravity and the spring force. And that's because they always it's like a closed loop. We'll talk about this a bit later, but they're always restored, right? A spring force is always restored. A force of gravity is always restored. Like there's no like, but when we're talking about non-conservative forces, you can think of like friction, air resistance, right? Things that like that aren't conserved basically, right? Like that are lost, like when objects lose like energy due to heat, that's also a non-conservative force. And like you can think of it as like stuff that removes energy out of a system, right? It's hard to put into words, but you can think of like a lot of examples. This is a good problem. Just So here's like an example problem that I think you guys should do, but and then here's like the summary of what we've done, right? So a compressed energy or a compressed spring can convert its potential energy into kinetic energy when it's released, and that's just it becomes 1/2 mv squared. It's the same for everything. So it could go from 1/2 kx squared into 1/2 mv squared. But you guys can go ahead and do this problem. A spring with spring constant K 300 newtons per meter is compressed zero point 0.2 meters. Find the energy stored in the spring. I think this is a pretty simple one. I'm just gonna go ahead and do it now. Um, yeah, so clearly we can just do 1/2 because the equation's given right here. We're trying to find the energy stored in the spring. So we can just do 1/2 times 300 times what? Zero point 0.2 squared. So we get 150 times 0.04. What is that? 15 over 10 times 4. What do you get? 3 over 2. You get 6, I think. I don't know. Someone can correct me if I'm wrong, but I got 6 joules of energy. Good. Okay. That's good to know. Everyone's getting that. Um, good, good, good. Okay, this is what I was talking about earlier, with the problem that we were doing. But so friction, I think you guys have a good understanding of what friction is, right? Whether it's like through context clues in this class or before, right? Friction's just the opposing force like between surfaces, right? So if you're kind of moving a box this way, friction is going to oppose it and move that way because the contact between the two surfaces, right? Does that make sense? Like why friction's a thing? And there's four types of frictions, but the main two you'll be dealing with are these two. Um, these two. Like these two don't really matter as much when you're working with it, but static friction and kinetic friction are the two main ones that are shown up in a lot of physics problems. So you can think of like static friction as like the one that opposes the first push of motion, right? If you're trying to push a box, right? Let's say this is you. Let's put it as Bob actually. Bob is trying to push a box, right? And he's putting force, right? But he hasn't yet moved the box. So he hasn't moved it yet because the static friction is great, right? He has to put more force. And let's say he still can't move the box. That means he hasn't overcome the static friction that's opposing this box yet. And then he finally puts a little more force and it starts to move. That means he has overcame the static friction between the two surfaces and he's able to move it now, right? And then kinetic friction is the friction that slows the sliding. Or like let's say Bob is pushing this box pretty easily now, right? Let's say Bob is pretty easily pushing this box since he's over the static friction. And now let's see he gives it one final push, right? And he pushes it with so much force that it slides over a few meters and then it stops. It starts to slow down because of that kinetic friction that this box is facing, correct? Since static friction was a thing that he got it to start moving, then he's facing kinetic friction now. It's also like pretty interesting to think with a tire. When you're thinking about a tire, what would you guys think? I'm actually gonna pose this question. Yeah. When you're in a car and your parents are driving, right? This is a great car. Oh my God. Okay, let's say this is the car, right? And you're on the road. Do you think your car is going through static friction or kinetic friction? Let's see what we think. Just type static or friction in the chat. Ooh, sorry. I'm seeing a lot of statics. That's good. It is static friction because this tire is constantly having to it's a new part of a tire every single time, right? So this tire is constantly having to oppose the starting motion of the road every single time. So it is static friction. Does that make sense to you guys? Why it would be static and not kinetic? Yes. Okay. Let's go on. Ooh, this is what you guys were talking about, or this is what I was mainly talking about, right? So when you're looking at the static friction formula, right? It's this looks a bit complicated, but I'll break it down for you guys, right? So um you can clearly see that this is equal to F sub S is equal to the force of the static friction is putting. Like let's say I'll draw Bob again. Let's say this is Bob pushing a box this way, right? But let's say this friction, sorry, let's say this friction, or the force of the static friction is greater than, oh yeah, and we're covering the normal force right after the friction, but, let's say let's say the force of friction, the static friction is too much, right? That means the coefficient of the static, so the coefficient of the static friction is basically just like it's dependent on the object, right? So this is not okay. I'll explain it in English though, right? Let's break down what the coefficient of static friction is first. So when you think of the coefficient of static friction, you're basically thinking about like what type of surface you're on, right? Like let's say ice. And when we're thinking about ice, it'll have a lower coefficient of static friction because you can slide a lot easier on ice versus let's say you're on like carpet. Carpet, it's harder to move something than on ice. That's because the coefficient of static friction on the ice is a lot less than it is on carpet. Does that make sense to you guys? So that's how you can think of what no, it doesn't. Okay. Um so let's say okay, let's not think about the coefficient of static friction as a variable right now. Let's think of it as like a surface. Like, like surfaces that you could stand on, like wood, carpet, ice, like sorry, not ice, but a skating rink. Um, what are some other surfaces? Cement, right? You guys know like the different type of surfaces, right? A bed, anything, right? Do you guys know a trampoline? Sure, anything. But you guys know that each surface, it's either easier or harder to push something on, correct? Like you can think about it kind of like realistically. You can push something a lot easier on ice than you can do on like cement, correct? Because on ice it'll slide and versus cement, it'll just stick, right? That's because that's because of almost it's somewhat because of this coefficient of static friction, correct? And you can kind of think it like because the coefficient of static friction is smaller on ice, that's what allows it. So you can kind of think of like you don't have to like think of the coefficient of static friction like an actual thing, but you can think of it as a concept that you can relate in the real world. Does that kind of make sense to you guys? If not, that's okay. I'll have Ethan try to put it in words in chat for you guys if that's easier. Because I'm trying to think of easier ways to explain it, but it's hard for me to like kind of think of it on the spot. But if it not in the still kind of okay. Ethan, do you have a better way to explain it in chat? Okay, while Ethan's explaining in chat, I'll move on from this slide because I know I'll have it posted in the I'll have it posted on the Google Classroom for you guys to see. But for right now, let's just skip it because this is a bit too much. If you guys end up getting it by Ethan's explanation, that'd be great. But if you guys don't, that's okay. I'll try to figure out some way to explain it next class. So, you know how we saw this though, the normal force? This was part of this equation. I didn't explain it. That's because we're gonna talk about it right now. So the normal force is basically like you can kind of think of it as an imaginary force that helps support. It's like a supporting force that helps exert some force on an object to keep it like on it, right? So like if you look like I don't know how to explain it in words, but this is a great drawing, right? If you just I'll even dumb it down a little more. I'll simplify it, right? Let's say you have a box. We know that there's a force of gravity acting this way, correct? But what's keeping the box on the table is called the normal force because the normal force is basically just pushing this box up against, and it's important. It's pushing it up against the table, right? Does that make sense? So like the table responds by applying a force equal to the block's weight and then equal and opposite to the block's weight, and the block applies a force equal on the table. No, the table's not the normal force. The table's what's kind of applying the normal force though, right? So we know that we know that the block is applying a force downwards of mg on the table, right? This table responds by applying a force onto this block to keep it on the table, correct? If the block was applying a force on the table, but the table wasn't applying a force on the block, this block would just go right through the table. So what's keeping the box on the table is this normal force that kind of opposes the box, right? Does that make a little more sense to you guys using the pictures, or is it still? I know the normal force is a bit easier than the friction, but I think friction and normal force are pretty complicated to understand because it takes a lot of like thinking. Does this make, is this like just make, is there any questions? Okay, okay, let me think for a second on how to explain this in a better way because I know I didn't explain it fully. So like, do you guys know Newton's laws? Newton has three laws. Okay, we have someone talking about it. Like Newton has three laws. The first law is basically that an object will stay at rest if the first law is basically an object will stay at rest if there's no force being applied to it, right? The second law is basically just force equals mass times acceleration. The third law is what is being applied in this case. The third law is that there's an equal and opposite force on like there's an equal and opposite reaction on like every force on every object, correct? So when we're thinking about it in this case, you're thinking of like this table exerting an upwards force on the block. That's what this normal force kind of is, right? Let's start with the block itself, right? Let's not like let me simplify, right? Let's think about this block. Let's say this block is on this table, correct? Bob is trying to place kind of, okay. Yeah, kind of like what you said, Sanchana. But basically, let's say Bob is holding a box. Bob holds a box, and then let's say oh, that's some long arms. Okay, I guess Bob has long arms. Let's say, and then Bob places this box on the table, right? When he places this box on the table, this box places a force downwards. Yeah. Let's say he's not human. But let's say like when he places this box on the table, this box will um, display a force downwards due to gravity, right? Because gravity is pulling it downwards, correct? But the point of the table is to make sure it stands up, correct? So this table's job is to apply a force upwards onto this box. So this box doesn't go through this table, correct? That's the whole point of a box, or that's the whole point of a table. So you can kind of think of this normal force as this table keeping this box up by applying the force upwards, right? And does that make a little more sense? Yeah, the table is pushing back with the same force. It's okay if you guys still don't get it. Like, I would rather you guys tell me that it's still not making sense than just than just saying yeah to. So if Bob is quite the Enderman, kind of leaning no. Okay. So I like, I'm just gonna like, Ethan, could you also is Ethan in call? Okay, yeah, Ethan is here. Ethan, could you also, yeah, it's basically Newton's third law. Um, so Ethan, could you also, like, while you're doing the friction one, could you also put the normal force in words for them to understand? But I'll try to, yeah, it's like Newton's, so the normal force is basically the table pushing up on the box. I don't think he's here. I see him in I see him in participants. I don't know what he's doing though. It's okay. I'll try to explain it one more time with a different analogy, right? We're gonna erase Bob for right now. I don't like Bob anymore, okay? Bob is gonna go bye-bye, right? We're gonna use Newton's third law, right? We're just gonna be using It was too loud for this whole thing. Okay. But let's use wait, yeah, let's use a ship, right? What is it called again? I forgot what this is called. Wait, sorry. A spaceship. Wait. A rocket, that's what it's called. Let's use a rocket. Sorry, guys. Let's use a rocket as an example, right? When there's a rocket being flown into space, the way this rocket is able to go up is because you know how there's gas that comes out of the rocket's like bottom, right? That allows it to propel upwards. Technically, without the normal force, this rocket wouldn't be able to go up because this gas is pushing downwards, correct? Out of this rocket. Does that make sense to you guys? Like the gas with the fuel that's basically pushing yeah, the fuel that's coming out of the rocket is going directly downwards and yeah, almost like propulsion, but like yeah, technically you guys could think of it as propulsion. But when a rocket is being flown into space, it's because there's this gas that's being pushed really fast and hard downwards, right? And what does a rocket do when this gas is pushed down and hard? What does it do? It flies up, right? It starts to go up. And basically, it's going up because this because the gas is applying the same amount of force on this rocket that it is on the ground, right? To go upwards. And this force that makes it go upwards is the normal force. Like that, sorry, the force that's being applied from the gas onto the rocket is the normal force. Is that does it's okay if you guys still aren't getting it because I know it's tricky. And Ethan did I guess it does look like a squid now, but Ethan did put a Ethan, did you put the friction one in? I don't know if I think you guys can also read Ethan's response if it um help you guys to understand. But if you guys still don't understand, I think just shoot us a message in Google Classroom. It's like the equation, like there's no equation for the norm. Like um there's no equation for the normal force technically because like if you think about it in this case, when there's a block, like when there's a force, you know how force equals mass times acceleration? And acceleration in this block's case is gravity, right? So it's just force equals mass times gravity, right? So if this block is applying um a force downwards with mass times gravity, then the normal force would just be the complete opposite. It would just be mass times gravity upwards. So it's basically like in some cases like this one, it's just the opposite, right? It does get more complicated, but for now, like just to understand the concept, you can think of it kind of like that. Ethan also put the static friction explanation if that helps. But don't worry too much about the equations. That'll come to you guys once you guys understand the concepts, because the equations aren't as hard as understanding the concept itself. But yeah. Okay, I think we should take I'll give you guys like a until 12 a mental break from that. Even because that was a lot. Oh my God. That's a lot for you guys probably. It's okay if you guys still didn't understand it fully. Just shoot us a message in Google Classroom and Lucas, Jethan, me, or Ethan. Like if you're not getting it from me or Ethan, then like Lucas or Jethan could maybe help you guys understand it a bit better in like different terms because we all have different teaching styles. You guys have until 3:12. Okay. Are we good to continue? All right, let's move on to forces. So, by now I think you guys know that a force is a push or a pull. Um, there's like forces is a very vague term. There's conservative forces and there's non-conservative forces, and I think we touched on this a bit earlier, but these are what determine whether mechanical energy, like the kinetic energy, potential energy, whether those are conserved or not in a system. So, conservative forces are forces where like the path is independent, right? So if you look right here, um, I think this is a great picture, but if you look right here, going from point A to point B, like it doesn't matter what path you took as long as you got to point A or from point A to point B, right? This is kind of what you can think of as conservative forces. Like gravity is a great example. Like it doesn't matter what path this object took, it still ended up reaching the ground from point A to point B. And same with the spring force, right? If you take sorry, it doesn't take up space, but um Ethan, could you look at the Google Classroom code? Sorry, back to what I was saying. So if you look at the also if you guys have like any questions like I would suggest sending them to Ethan because when I'm teaching I would prefer I would prefer your an questions to be answered as fast as possible. But if you also look like back to what I was saying about a spring, if you look at a spring, it's kind of the same thing. It doesn't matter what path you took because it's the same, you know. Like it'll have the same point either way, if that makes sense, right? The energy is fully recoverable. And like there's no energy basically energy conservative forces, there's not gonna be any energy lost. These are some great examples of let me delete that. These are some great examples of conservative forces like lifting an object, increasing its or for gravity, just lifting an object from to some height and then dropping it. There's technically no energy lost. It's just being converted from potential energy to kinetic energy. Um, Same with the springs, going back to Hooke's law. That's just basically stretching, like stretching or compressing a spring stores its elastic or potential energy, but then it gets recovered when you release it and it goes back to its normal shape, right? Those are the formulas for like okay. Non-conservative forces, on the other hand, are dependent on the path that it took, right? So, I think like the best way you can think about non-conservative forces are like things that take energy out of a system, such as like friction, air resistance, or like something like something other than like something that's pushing or pulling with energy loss. So if you look over here, when there's like let's say this is a rubber ball and it's bouncing on the ground, right? When it contacts the ground, like some like non-conservative forces in play is like the sound it creates, the heat when it contacts this ground, the friction it creates, and like anything like that, correct? Those are all non-conservative forces. But if there were no non-conservative forces, then this ball would just bounce back to the same height. But I'm sure if you've noticed when you bounce a ball, it gets lower and lower every single time you drop it, or every single time it bounces, right? That's because of like the noise, the heat, the friction, everything like that. That's what contributes to lowering the bounce of something every single time. Um, so this is just a comparison. Like these are like I think these words kind of overcomplicate what it actually is. Like I'm not sure, but like if I was learning this for the first time, I wouldn't get it from what this is said on the slide, but does it make sense when I explain it in English? Yeah. It's basically just anything that keeps energy versus something that takes energy out, right? Mm. So there's two examples up and then I think we just covered this practice question. Oopsies. Do you guys like know what forces that could cause the energy to be lost? Just name like a few, one or two in chat. Yeah. Yeah. Basically, conserved energy keeps the same amount of energy in the system, and the non-conserved energy like takes energy out or like makes the system lose energy, basically. Ooh, conservation of energy. Is this where we stop for today? No. Huh. Oh, that's just part of it. Okay. Okay, that makes sense. So basically, this goes hand in hand with the conservation of energy. The law of conservation of energies just states that energy cannot be created or destroyed. It can only be transformed or transferred, right? So basically, when a ball's bouncing and it starts to bounce less or it starts to get lower and lower, the energy is not disappearing in that case, right? It's just being transformed into something else. It's just like the heat or sound is the form of energy that it takes, right? So like when you're thinking of a system and if you think that the energy is disappearing, it won't ever disappear, right? It's going somewhere and you just don't know where it's going, right? It's one of the simpler laws. I actually like the law of conservation of energy because of how simple it is and it's very practical as well. Like a lot of the times you'll use it when you're working with like a roller coaster and you won't even know, right? It indirectly states that like yeah, actually this is pretty good. This is a segue into this, right? So we know that energy can be K E plus and PE, right? So a systems can have both KE and PE, right? Or kinetic energy and potential energy. Like a roller coaster at its midpoint has, or let's say a roller coaster up here has both kinetic energy and potential energy, right? So kinetic energy plus potential energy equal, I don't know, I put a line, equals the total energy. I'm just gonna say TE, total energy, right? But then down here, remember that that energy cannot be created or destroyed, right? So right here, there'll be the same amount of energy, but like it'll be either more in PE or it'll be more in kinetic energy, right? So it would just be right. We already defined this. Let's put sub one, right? This is at the first, the one just means at the first spot. The second, so the kinetic energy and potential energy at the first spot will always equal the kinetic energy plus the potential energy at the second spot. This is always going to be true, right? Whether it's through, and then you can, whether there's non-conservative forces at play that are taking energy out, but yeah, like, you know what I mean? In an ideal system in an ideal system, which we will be using kinetic energy, the first initial point of kinetic energy plus potential energy will always equal the second point of kinetic energy plus potential energy. Moving on to power. So power is basically like you've read like watts, right? If you're looking at a light bulb, it'll say like how many watts it produces. That's basically it's telling you how much power it's producing, right? And a watt is just equal to a joule per second, right? And you've heard of joules before, right? Joules is equal to energy or work, right? Energy slash work. So if a watt is just a joule per second, a power, since watt is equal to power, power is just equal to energy over time, right? In seconds, correct? Does that make a lot sense logically? Since power is equal to watt and energy is equal to joule, and since power is just watt or watt is just joules per second, you just get energy over time is equal to power. And here's the thing. I mean, yeah, you can write it in your notebook. I don't expect you to remember it after like the first time, but once you use it a bit, it'll stick. Um, so basically, this is just reiterating, right? If power is equal to energy over time, if power is equal to energy over time, you just multiply time on each side to get power times time equals energy, right? It's simple algebra, right? Oh, I don't know why I crossed that out. It's algebra, so you know, yeah. So if you're using a 2 kilowatt hour, if you're using a 2 kilowatt heater and you use it for 3 hours, the amount of ever energy you're producing is 6 kilowatts per hour. Sorry, 6 kilowatt hours. And if you guys don't remember it, that's okay. Just write it down in your notebook or paper, wherever. Um, sorry. Do problem one and problem three. It's still kind of confusing. What do you guys think is confusing about the what do you guys think it's like what part of like power do you think is confusing? Give me a second, sorry, my computer is running out of battery, so let me just get a charger. Were you just saying problem three was confusing? Or like the concept itself is confusing? Because if the concepts are confusing, then I can try to explain it more. But if the problems are confusing, we can go through that together. So basically, power is just how much energy it's using per second or per minute or like whatever unit of time, right? So I'll put the equation up here. So when you're thinking of like, let's say you're thinking of a light bulb, right? When you're thinking of a light bulb, and you're thinking about how much power it produces, you're gonna think, oh, how like you're gonna think, oh, how much energy can it produce over like a certain time period, right? So I don't know if this is technically true, but let's say a light bulb says 50 watts on it, right? It's just saying it's producing 50 joules per second. I don't know if it's per second or whatever, or I don't know if it's a joule or a kilojoule or whatever, but I'm just gonna use like joules per second as my units, right? And let's say this light bulb, for example, is advertised, let's say this light bulb is advertised to produce 50 watts, right? And you go in the store and you see the 50 watts. You're gonna think, oh, this light bulb is a kilojoule is just 1,000 joules. It's like to shorten it, you don't say 1,000 joules, you just say kilojoule. Um, that's a kilowatt as well. They're just bigger versions of the one, but I mean maybe. But so back to like the concept itself. Like that's like the power is just like, does that kind of like make sense to you? Like if we work through a problem, no, kilo is like a prefix. Kilo is like not only for kilograms. So the mass for kilograms is just a gram, right? But 1,000 grams is a kilogram. It's the same thing here. A, so you usually think of kilograms as it seems normal, but it's actually a gram. It's 1,000 grams, right? Same thing with a kilojoule. When you're talking about a kilojoule, you're just thinking of 1,000 joules. Kilogram just seems more normal because we use it more day to day. But like a centimeter is 100th over a meter. Let's just go through these problems really quick and then I'll call it for today. But so if we know joule is energy, correct? So if P equals energy over T, and we know we're counting, we're talking about T in seconds over joules, right? So it's just 1,200 joules over 6 seconds, which just equals what, 200 watts in this case? So you can also just say it's the power output is 200 joules per second. If to your energy output is 200, you're outputting an energy of 200 joules per every second you leave it on. So for every second that the crane works, it's doing 200 joules of energy. No, we're not gonna have a final test. No. We'll have review days, but we won't have final tests. We don't do that. But for the third question now. Okay, this is a bit harder. This is a lot harder, I think, problem three. So in this case, we need to find out what we're given the time, but we need to solve for the energy, right? So we're given 2 seconds Again, we want to always identify our variables, right? If 10 kg, okay, so we have mass, right? If you have mass, which is 10, ooh, I don't like this at all. What the happened? Okay. If we have 10 kilograms, which is equal to mass. But then we have 2 meters, which is, let's just say, height, because it's raised up 2 meters. And if it says assume gravity equals, I'm just going to use 10 for right now. But if we were saying gravity equals 10, and then we also have time, which is equal to 2, right? You would think that you wouldn't have the necessary things to solve this, but you actually do because you have a formula, remember, right? Since PE is equal to joules, right, or equal to energy, we can use that, right? Because we know PE, the potential energy, is equal to mgh, right? And guess what? We have all three things of mgh that we need here, right? So if we multiply that out, we get 10 times 10 times 2 over 2, right? Because you're close, but if you have a class or if you have something else, feel free to leave, but I'm just gonna finish up this problem real quick. So 10 times 10 times 2 is, sorry, the 10 times 10 times 2 is equal to 200 joules, right? But remember, watts is equal to joules over uh time, right? So then you just get 2, so then you just get 200 over 2 equals 100, right? So you just get 100 watts or 100 joules per second. So this, if you kept on lifting this box, you'd be doing 100 joules of energy per second you were lifting this box. Let's say you were lifting this box for 4 seconds. You'd be doing 400 watts then. It would be 400 joules for 4 seconds in total. Sorry, 400 joules in total, correct? Does that make sense? Sorry. Yeah. Okay. If you guys have any questions, feel free to stay, but if not, then you guys can go ahead and leave. That's it for today.